I'll tell you what, let's measure current with an Arduino. How do we do that? How do you do that accurately? And you, because there are different ways of measuring current, obviously. You can use a multimeter and interrupt the circuit and put the multimeter in amp mode, and you can measure current that way. You can take an amp probe or a magnetic, amp probe and put around the wire. You can measure that way. But what if you want to have a computer monitoring the current of something and either displaying that or programmatically reacting to it, like over, under, keeping track of your watt hours that you're using, doing whatever, but you just want to do something and you want a computer to monitor it. And since we love Arduinos here on the BRMBLOG, let's see, how do we measure current using an Arduino? Now, what's in front of you is a schematic that's taken me a little while to figure out, because I've tried measuring current accurately a number of times, and I would always make little mistakes with it. First, I would use, there are different methods to do it with a resistor in circuit on the low side or the high side. What I've got in front of you is it's on the high side, the resistor is, and let's just go through it. And then what we do is we measure the voltage off of that resistor, that known resistor. And let's go through it here real quick, and then we'll look at the real version of this. We have our power supply here. Doesn't really matter what it is. It's just supplying our power to everything. It can be 5 volts, 12 volts, whatever. I have a load resistor here, and it doesn't. These load resistors doesn't matter what they are. I've just got enough in there to make what we're measuring, meaningful. I don't want to put a mega ohm in there and try to measure that. That's a whole different story. These are high wattage resistors, low value, just so I can get enough current going through there so we can make a decent measure of it. Then we have this resistor, and it's a 1 ohm at 1%. This is the most accurate one I've got. If I was really doing this for a customer or something, these would all be 0.1% or 0.05%. And they would be, I would do the same thing I'm doing here. I would just have higher precision, more precise parts. But what I've got currently in stock, in my own stock, is a 1 ohm, 1% resistor, and this is going to be the resistor that we measure across, and I'll explain what this is. We're going to measure the voltage across it that forms across it when the current goes through it. And then the current goes out through the load, and I've got a couple of big resistors here just acting as the load to ground. So you got your power supply, you're going through your load. This load could be anything. This is a resistive load. This could be a more complex load. It could be a reactive load. It could be another DC to DC converter. It could be anything. But this is going to be a resistive load, and then it just goes to ground. So we have a current going through to ground. Now, this 1 ohm at 1% is the both sides of it are going to be across a instrumentation amplifier. And let me show you an instrumentation amplifier. This instrumentation amplifier, this is actually the one I'm actually using. I hope you can see that. That's coming off awfully blue on my screen. Can you see that? Whee. But that the pins 2 and 3 that I've got here, pins 2 and 2 and 3 across our resistor that the current goes through, our shunt resistor, it's called. That's this pins 2 and 3 of this instrumentation amplifier. An instrumentation amplifier is a difference amplifier, and internal to the chip is this right here. That's what makes an instrumentation amplifier. And you can go out and look up and you can find scads of information on exactly what an instrumentation amplifier is, the types of things it's used for. It has a high common mode voltage rejection ratio. There's all kinds of benefits to an instrumentation amplifier. And it also makes good for current sensing. The pins 2 and 3, so we have this resistor I'll explain in a minute. So we have our resistor tapped off, pins 2 and 3 here, and we have an output pin 6 is our output, and that's going to be, it's going to be, basically you're going to see a voltage between these, and this is going to amplify the difference between pin 3 and pin 2. It basically takes pin 3, subtracts pin 2 it, and multiplies it by gain, and then that's the output. That's going to be your output. Now this resistor between pins 1 and 8 on this little chip, and let me show you the chip, or just a little more physical here. This is the INA128 PA IC low power instrumentation amp, 8-pin DIP, and this is from Texas Instruments. And I tell you, Texas Instruments, I just love dealing with them. I love ordering their parts. They get them to you so quickly. You order 1, you order 2, you order 10. I mean, it is there the next day or second day. They get them to you so quickly, and their service is fantastic. But anyway, this is the INA128 instrumentation amplifier. This is what it looks like inside. This is the gain resistor. So when you set this gain, you go by this formula here. Now I don't know if you can see that formula, but the gain of this whole unit, this whole block, is equal to 1 plus 50K divided by that resistor. Well, I put a 50K resistor there. So 50K divided by 50K is 1, plus 1 is 2, so I get a gain of 2. So whatever difference between here and here is going to be multiplied by 2, and it's going to come out here. So if this is 0.1 volt difference between here and here, it's going to get multiplied by 2. It's going to be so I'm going to see 0.2 volts out here. Well, then when I send that to my Arduino, I can handle that. I can divide that by 2 again to get an actual number. So that's where the Arduino will come in. But we'll get to the Arduino. And then you have your V minus, which I've got is minus 5 volts, and V plus I've got is plus 5 volts. Let's see. This is the IN128, the functional block diagram, and now I just made it into a big block. I didn't put all of the triangular shaped amplifiers, op amps in there, mainly just for clarity. Here's my V plus, V minus. Here's my gain, which is 50K. Here's my gain equation, 50K over 50K plus 1 equals 2. Now here's where I have some error. I've introduced error here. I'm using a 5% 50K resistor because that's all I've got. That's the closest thing I've got to it. So I'm going to have an error introduced there that I could measure it myself, and I could take it out in programming if I wanted to, and that would be like some initialization parameter to take that out. I didn't do that because that's not the purpose of this. The purpose of this video is to show how to measure current and do it fairly accurately. Then if you want to get into minute down to the highest precision, then that would be like another video where we can get into all the techniques used to improve your precision. of your, and improve your accuracy, I should say, of what you're measuring. But this is pretty good. As you'll see, this ends up being a pretty accurate way to do this. So your current's going through here. You've got your voltage. That gets doubled because I have my R gain. That gets doubled in the gain, and then that goes to V out, and that goes into Arduino into A0, into analog A0. And then I share common ground with them. And that goes into analog A0. Well, then I can just programmatically, I can use A0's input, and then I can do whatever I want, and we'll see that. So that's the schematic. That's basically what I'm doing. Now let me take that away. Now I just wanted to show you. Now I've already had learned how to do this, but the kind of places I went to learn was, one, data sheets to learn how these work, how these functions. And you don't have to use instrumentation amplifiers. I use them because I like them. They're easy. There's a low component count to them. They do a lot of things internally, and if you can reduce your component count, you reduce board space, you make your circuit is cheaper, less cost, so it improves your profits or decrease your cost to your customer. And I was just going down here. I want to show you some of these things. An instrumentation amplifier, microphone, hydrophone, thermocouple, used for all kinds of, for sensitive, low signal sensitive pickups. And they've got, there's a Wheatstone bridge amplifier, low voltage operation, AC coupled instrumentation amplifier. So they've got a lot of, you can learn a lot about how to use an instrumentation amplifier just from the data sheet. And I'll try to link this into the description. Just have to remember to do that. This is funny. They've even got an ECG. You can even use these to ECG amplifier with a right leg drive. And I was going to do this at one point, but my wife wouldn't let me. She thought I would electrocute her. And I suppose I could have done it on myself, but you know, I needed a guinea pig. So they even show you how to do an ECG with this. That would be fun. You know what? That would be fun. I don't have the OPA 2131. I've got the INA128, but to order these two and then put this together, I mean, look at the small component count. Now probably the pads would be the most expensive thing, and you'd have a common mode twisted pair probably would be fine here. But probably the pads going to your skin, which I noticed you can buy those on eBay now with the conductive gel, would probably be the most expensive part of that. Anyway, I didn't mean to get off on that. And then they show you how to implement that onto a circuit. The best way to put your bypass capacitors and etc. But let me zoom back up. Zoom back up to where we were. Here's the chart of your gains. And we're just looking at the IN128 side right now, because that's the one I've got. Desired gain of 2. What do you want your RG to be? 50K. Well, mine's like 49 point something. I measured it. It's 48 point something. So I'm introducing error there. So it's going to be, actually gain is a little worse, or a little off. But that's okay. It's close enough for what we're doing. And one of the places you can learn, I'll also put this into one of the types of places that I learned how to measure current was, this is EE Times, and there's thousands of articles like this, or hundreds, whatever, but this is one of the particularly good ones. because it shows you operational how to measure current on the low side and the high side. The low side is when you measure it when your load is between your plus and your measuring. Your high side is where I had it, where my shunt resistor was up above the system load. And here they do it with an op amp, and they give you, it looks like, some resistor equations anyway, so you could come up with your resistors. Your key is your shunt resistor there, and the precision of your shunt resistor is a big key. They've got another one there, effects of parasitic and ground. Here's a difference amplifier, which is built into an instrumentation amplifier. A difference amplifier is built into it. And here they use a high side with a difference amplifier. And the whole time I've had that, I apologize, I've had that off. Here there's low side sensing, and then they even talk about an instrumentation amplifier right there, and that's what we're going to be using. Now, I didn't get this from this article, but I read and studied articles in the past where I was able to put this together. And so let's take a look at the circuit itself. We've seen the schematic, but let's take a look at where I built it and what it looks like, and then what the meters are telling us. Now, this is the circuit, the actual physical circuit. It's probably not going to have a lot of meaning here. Where's my pointer? Just because it's kind of, it's jumbled up all together the way you do circuits. But I'll try here with the, you can see where the chip is. The chip is here, and pins 2 and 3, which are these two green wires, they come over here and they go back to this resistor. This resistor is our shunt resistor. Let's see if I can get in there. This has such poor automatic focusing. That green resistor is our 1% 1 ohm shunt resistor. And I had it, I built a power supply one time. I never built it up on a PC board. I just built it on a breadboard. And that's what I was using for my current limiting, is when I would detect, I would use a difference amplifier to detect the current coming out, and when it reached a preset level that was set by a knob, basically, it was a rotary encoder, because a computer was running it, a little small, actually it was a PSOC computer was running it, and the rotary encoder would set the value, and when it got over that, then it would start reducing the voltage down, and it wouldn't let the current go over the value. But anyway, that's where I come up with, that's why I had these. And so this is the current shunt. So you're going to have your sampling wires, which are these two green wires, one here and one here, are going to come over, and they're going to go to pins 2 and 3 on the instrumentation amplifier. I've got load resistors, which are these big ceramic resistors. These are my load resistors, and they're just acting as a dummy load for this. So so what I want to do is I want to say, well, okay, I do have a multimeter in circuit with it, because I want to see how accurate this is. And what is that telling me? So let's look at that. What current is going through there right now? Well, the current that's going through that circuit right now, through that shunt resistor, is 0.242 amps, 0.24 amps. So, almost a quarter of an amp. So 0.243, 0.242. That's the actual current going through there as read by this meter, as measured by this meter. So what does our, and I'm just going to pan over, and what does our the output, which is, if you remember, the output of is pin 6 on our circuit here. Let me pan back a little bit. Pin 6 of our circuit, that's our V out, and that's the one that's going to go to Arduino. So what does it say? What's coming out of there? Well, I've got that measured over here with this nice BK precision meter, and it says 0.4988. It's just about double the actual measured current that we're showing through there. That's the voltage coming out of pin 6 out of the instrumentation amplifier. So there's our gain of 2. If you multiply this by 2, you come up with a pretty close number, and that's why I say I've introduced error by having the 5% components in there. The gain resistor is a 5% component, and so I didn't have a 50K 1% or 0.1%. That would be more accurate if those other resistors were set, or the gain resistor was set more accurately. So I've got 0.4981 volts coming out of there. All right, coming out of pin 6. Well, what am I going to do with that? Well, I'm going to, let's back up here. And this is why you need multiple Arduinos sitting around, so you can do things like this. I've got the wire. You see this wire here? That's pin 6 wire, and it's coming out of, and that looks awfully out of focus. Is it that light? Hang on. Here we go. I've got pin 6 coming out here, going to A0, and if you're familiar with Arduino layout, that's pretty obvious. That's A0 going into there. So there's that 0.5 volts, or that 0.4981 whatever volts coming out of there. That's going into A0. This is just a ground wire. This is just a share, so they'll share common ground. And that's it. That's the only 2 wires I've got going over there. Everything else is going to be a program. So now I've measured current. I've got it fairly accurate. For the purposes of this film, of this video, it's fairly accurate. We know that we can make it more accurate by getting higher precision resistors. And now we've fed that into this Arduino here, and let's go look and see what it tells us. Okay, this is the data coming out of the Arduino. Which I have a program running, and I'll show you that. But this is the data coming out of the Arduino, and it's got 0.25. Well, what did we see over on the Radio Shack multimeter was 0.241 amps. And what did we see on the BK Precision was roughly 0.5 or 0.498 volts. So in the program, I just divided it by 2, because since I had a gain of 2, I divided it by 2. And we get down to about what our current is. So our current is approximately 0.25. So we have a current measuring device. We're measuring. This would be good enough to measure, coming out of batteries, coming out of things that you wanted to do some your plus or minus 5% kind of stuff. That's where I would classify this. And it took me 20 minutes to put it together. So that's about what, the effort I put into it. And it took another 3-4 minutes to get the program together. So that's that kind of effort. This is what you're going to get. If you want to get more precise, then you're going to need to order 0.1% resistors, and you might need another compensation. I didn't put the decoupling caps on the power supply. You probably need to do that. And so you need to do techniques. I don't have a twisted pair going over from the instrumentation amplifier to the Arduino. I've just got a couple of DuPont wires hooked together, put over there. So you're going to need something like that. You would want that to be shielded so that you would have a more accurate presentation there of the voltage. But given all of that, we're looking at 0.25, and if we swing over, just to remind us, 0.241 doubled 0.49, doubled, which were our voltage produced. We gather that into A0, we divide it by 2, and we get 0.25 out there. So we have we're running a 1/4 amp through that wire, and the Arduino knows it now. Now we can do anything we want with that, and we can. If I wanted to, I could take measurements. I could get exact values of that gain resistor, and take those errors into account, and then put those into the formula and do that. I prefer not to do that. I'd prefer to have 0.1% accurate resistors. I would prefer that in the hardware it be accurate, and then anything left over, then programmatically take it out, the error out, and make adjustments for it. But you could take those values into account now, those error values that are being introduced, and you could pretty simply put them in the formula. And I'll show you the formula, which is very simple, and put those in there as error values, and you could come out with a more accurate figure. You could get that down to 0.24 whatever. But there we go. That is how we do it. Here is the program. I found this on the web, and I just modified it to suit. I'm trying to find out who did this so that I can attribute. I don't see who wrote this code, so I can't attribute. It's on the Arduino website, though, the actual Arduino.cc website. And it's just their first example, read an analog voltage. And when you can cut and paste a little code and then make some modifications, that's what you do. Because in real life you have dates, schedules you have to meet. You've got to make progress in a project, and if something's already been done and you can use it, legally, of course, and use it ethically, of course, then do it. There's no reason to reinvent the wheel. If you want to just go through the exercise to learn it yourself, which I didn't need to do this to learn it. I know how to write this code. I've written it many times, but I just don't see a reason. I don't see a good reason to sit down and rethink through it when it's already out there. But anyway, I guess I'm arguing something there that doesn't need to be argued. We do the serial begin thing because we're going to be printing out the values that you saw. We do an analog read. We take we set our voltage to the sensor value times 5 divided by 1023, so that we set it to a voltage value. And then now what I added to that was, let me pull up mine. Probably should have done it to begin with. What I added to that was just simply this divide by 2 here. So so that divide by 2 brings it back down to what the current is. And when you look at the serial monitor again, that's what you get as your output. It's 0.25. So we now have an Arduino that reads a current. Now, do I want to, let's see, I guess the next step would be I'm not going to do this here, but your next step would be you'd want to characterize this. You would want to get a set of resistors, low value, and you'd want to drive this up to, an amp or 2 amps or down to 10 milliamps and see what kind of characteristic that you would get out of your measurement. How much confidence do you have that this can measure 10 milliamps? How much confidence do you have that this can measure 10 amps and still be accurate? That would be the next step. We're not going to do that here. That's a whole different video and set of tasks. But anyway, that would be the next step that I would do. Well, thank you for watching, and I hope you enjoyed that as much as I did.